channel. So this will be today's topic. My name is Aditya. Let's start. Talking about CNN, we should first know that what is CNN? CNN stands for Convolutional Neural Network, CNN, or ConNet, a type of multi-layer neural network that is meant to discrete visual pattern from pixel images. In CNN, convolution is referred to as the mathematical function. It's a type of linear operation in which you can multiply two functions to create a third function that expresses how one function's shape can be changed by the other. In simple terms, two images that are represented in the form of two matrices are multiplied to provide an output that is used to extract information from the CNN, from the image. CNN is similar to other neural networks, but because they use a sequence of convolution, they add a layer complexity to the equation. CNN cannot function without convolution layer. Taking a deep dive into the typical CNN architecture, you can see that image is represented in binary, that is 0 and 1. And you have multiple layers, like you go through a pooling layer, a flattening layer before you train your neuron. So as you can see below, you have an input image, a convolution layer, a pooling layer, a dense layer. Talking about convolution layer, what is a convolution? So they are also called CO and VCon. They are the foundation of CNN and they are in charge of executing convolution operations. The kernel filter is the component in this layer that performs the convolution operation. Until the complete image is scanned, the kernel makes horizontal and vertical adjustments dependent on the stride rate. The kernel is less in size than a picture, but it has more depth. This means that if the image has 3 RGB channels, the kernel height and width will be modest spatially, but the depth will span all 3. As you can see in the diagram, we have an input image that goes through the image patch, that is the local receptive fields, then through the kernel, and then this is how you get your output. Talking about the pooling layer, that's POL. This layer is in charge of reducing dimensionality. It aids in reducing the amount of computing power required to process the data. Pooling can be divided into two types, maximum pooling and average pooling. The maximum value from the area covered by the kernel on the image is returned by the max pooling. The average of all the values in the part of the image covered by the kernel is returned by the average pooling. Fully connected layer, also known as FC. The fully connected layer works with a flattened input, which means that each input is coupled to every neuron. After that, the flattened vector is sent via a few additional FC layers where the mathematical function operations are normally performed. The classification procedure gets started at this point. FC layers are frequently found near the end of CNN architecture if they are present. About activation function. The last fully connected layer's activation function is frequently distinct from the others. Each activity necessitates the selection of an appropriate activation function. The softmax function, which normalizes output real values from the last fully connected layer to a target class probability where each value ranges between 0 and 1 and all the value total to 1, is an activation function used in multi-class function problems. Dropout layers. The dropout layer is a mask that nullifies some neurons' contribution to the following layer while leaving all others unchanged. A dropout layer can be applied to the input vector, nullifying some of its properties. However, it can also be applied to a hidden layer. Nullifying some hidden neuron dropout layers are critical in CNN training because they prevent the training data from overfitting. If they aren't there, the first batch of training data has a disproportionately large impact on learning. As a result, learning of traits, the only in later samples or batches would be prevented. The LeNet architecture. The LeNet architecture is a simple and modest, making it ideal for teaching the fundamentals of CNN. It can even run on the CPU if your system lacks a decent GPU, making it an excellent first CNN. It is one of the first and most extensively used CNN designs, and it's been used to successfully recognize handwritten digits. The LeNet 5 CNN architecture has 7 layers, 3 convolution layers, 2 subsampling layers, and 2 fully linked layers, making up the layer composition. A pictorial depiction is there below. As you can see, you have a 32 into 30 input size of an image. You go through the convolution network. That is the first one, C1 feature maps, S2 F maps, C3 F map 16. Every time the size is being reduced until you get your output layer. So you can see that subsampling keeps occurring in between all these layers. The AlexNet architecture was extremely similar to LeNet's. It was the first convolution network to employ the graphics processing unit, GPU, to improve performance. Convolution filters and a nonlinear activation function termed ReLU are used in each convolution layer. Max pooling is done using the pooling layer. Due to the presence of fully connected layers, the input size is fixed. The AlexNet architecture was created with large-scale image datasets in mind, and it produced state-of-the-art results when it was first released. It has 60 million characteristics in all. Talking about the VGGNet architecture, while prior AlexNet derivatives scores on a similar render size and strides in the first convolution layer, the VGG takes a different approach to CNN. It takes input as a 224 into 224 pixel RGB image to keep the input image size consistent for the ImageNet computation. The authors clipped out the middle 224 into 224 patch in each image. The receptive field of each convolution layer in VGG is quite tiny. The convolution stride is set at 1 pixel in order to preserve spatial resolution after convolution. VGG contains 3 completely connected layers, the first 2 of which each has 4096 channels and the third of which has 1000 channels, one for each class. Due to its adaptability for a variety of tasks including object detection, the VGG CNN model is computationally economical and serves as a good baseline for many applications in computer vision. Talking about some of the CNN architecture, following are some of the advantages of a convolution neural network. CNN is computationally efficient. It performs parameter sharing and uses special convolution and pooling algorithms. CNN models may now run on any device, making them globally appealing. It finds the relevant feature without the need for human intervention. It can be utilized in a variety of industries to execute key tasks such as facial recognition, document analysis, climate comprehension, image recognition, and item identification, among others. By feeding your data on each level and tuning the CNN a little for a specific purpose, you can extract valuable features from an already trained CNN with its thought weight. So with this, I'll finish my video. Thank you all for watching.